अभी मैं कर रहा हूँ, ये गो लाइव चला गया हूँ मैं, अब यूट्यूब पे मेरे को लाइव दिख रहा होगा, ठीक है। यहाँ पे अब एंड स्ट्रीमिंग आएगी ये।
अच्छा ठीक,
बस आपको इसको ऑफ करना है,
ठीक है।
और इस सॉफ्टवेयर में चले जाके यहाँ पे स्टॉप स्ट्रीमिंग करके एग्जिट कर लेना।
अच्छा
तो ये 2 चीज़ें करना पड़ेगी, बाकी अब सर जो भी करेंगे वो अपने को लाइव में दिखेगा।
ठीक सर।
ये सर आपकी विंडो ओपन है। हाँ,
कोई दिक्कत नहीं सर, ले लेगा वो, सेंस कर लेगा, ऑडियो ले लेगा वो।
आप नॉर्मली बोलेंगे तो ले लेगा ऑडियो।
Okay, so good evening to all of you. Welcome to day 4 lab session 3, and this session would be on the FED heterostructure. So in the morning session I showed a few results which I obtained through the simulation, and now I'm going to demonstrate those results in this tool. So, as I told in my morning session, the ferroelectric capacitor or a ferroelectric material can be mathematically modeled by an equation which is known as Landau-Kholotnikov equation, which is basically Vf equals to alpha Qf plus beta Qf cube plus gamma Qf to the power of 5. But here for simplicity, I have considered my constant gamma equals to 0, and I have taken the equation only up to 3rd power. That is, now the equation reduces to Vf equals to alpha Qf plus beta Qf to the power 3. So now we have to plot Vf versus Qf characteristic for a ferroelectric capacitor. And I have on my x-axis as the voltage across ferroelectric, and on y-axis I have the charge across ferroelectric. Now, if you can see, this I have written one equation, minus 1.4991 into 10 to the power 14 y plus 8.073 into 10 to the power 41 into y to the power 3 equals to x. Here my x is the voltage applied, and y is the charge, and the coefficient of y is alpha and coefficient of y cube is beta. Now alpha is the anisotropy constant, which is obtained by the expression minus 3 root 3 by 4 EC into PR, where EC is the corrosive field and PR is the remanent polarization. As I have discussed today in the morning session, the value of corrosive field and the value of remanent polarization for my material, which is lead zirconium titanate. Now, using that value of corrosive field and remanent polarization, I got the mathematical value of alpha and beta. And these values which are over here, this is for TFE equals to 30 nanometer. So here you can see I have got the value of alpha as minus 1.4911 into 10 to the power 14 and beta as 8.073 into 10 to the power 41. So my equation becomes alpha into QF plus beta into QF to the power of 3 equals to VF. Now, here what I have done, I have plotted this particular graph. Now as you can see, I will zoom it a little bit. So you can see in this particular region, the gradient or slope of this particular characteristic is negative. So as I am increasing the voltage, my charge is decreasing. So that shows me the presence of negative capacitance in my ferroelectric oxide, because here I am increasing the voltage and the charge is decreasing. So this this characteristic with green line is for TFE equals to 30 nanometer. Now next I'll move on to TFE equals to 60 nanometer. Now the same way how I calculated my value of alpha and beta in my previous case, here I'll calculate the value of alpha and beta for my TFE equals to 60 nanometer. Similarly, I have extracted the value of alpha and beta for this particular thickness. So here I got the value of alpha as minus 2.982, which is into 10 to the power 14, which is alpha, and 1.614 into 10 to the power 42 is beta. Now here I have plotted this characteristic, and this is in orange color. Now here also you can see in this range, if you see the gradient or slope of this characteristic, it's negative. So means I'm increasing the voltage.
Value for this curve is
TFE equals to 16 nanometers.
16 nanometers.
16 nanometers. So previous one, the blue one was for 30 nanometer. This is for 16 nanometer. 16 nanometer ferroelectric thickness. Okay. So now you can see the slope or gradient of this particular line is negative in this particular region. So as I'm increasing the voltage, charge is decreasing. So which confirms the presence of negative capacitance. Next, similarly, the thing which I did for 30 nanometers and for 60 nanometers, the same thing I am going to do for 90 nanometers. So again, I have repeated the same process. I obtained the value of alpha for TFE equals to 90 nanometer as minus 4.47 into 10 to the power 14, and beta equals to 2.422 into 10 to the power 42. And I have plotted this characteristic. So this equation is alpha QF plus beta QF cube equals to VF. Now here you can see in the violet line. So for this particular range, as I increase the value of voltage, the charge decreases. So this confirms the presence of negative capacitance. And the last one, I have obtained the values of alpha and beta for TFE equals to 120 nanometer. So for TFE equals to 120 nanometer, alpha equals to 5.964 into 10 to the power 14, and beta value as 3.2295 into 10 to the power 42. Again, as you see the characteristic, as I increase the voltage, the charge increases. So here I have restricted myself up to the graph up to TFE equals to 120 nanometer. There is a particular reason behind it, because after this I will be going for FED heterostructure, and if I increase my thickness beyond 120 nanometer, because in the upcoming graphs I have taken the dielectric thickness as 1 nanometer, the hysteresis starts appearing in my characteristic. That's why I have stopped here at 120 nanometers. So this was about the charge versus voltage characteristic for isolated ferroelectric capacitor, which I have obtained by solving LK equation, which is known as Landau-Kheltnikov equation. And you can see the signatures of negative capacitance in these graphs. Similarly, like what we did for charge versus voltage, similarly we are going to study for U versus Q, energy versus charge.
So same phenomena is happening in reverse direction also. Heavy increasing the reverse voltage.
Yes.
Again the value of
So
increasing. That's why you have taken the magnitude part.
where sir?
In negative part.
हाँ.
तो यहाँ आप देखिए ना, यहाँ भी
So
अगर आप कर रहे हैं.
yes, it's falling. The gradient is negative here.
Yes.
So that tells me the presence of negative capacitance over here. So similarly, like for charge versus voltage, I'll see U versus Q.
Yes.
So I'll move on to the graph number 2.
So just tell the steps.
I'll tell. Now, like in positive dielectric capacitance, the energy stored in the dielectric capacitance U is given by Q square by 2C. Q square by 2C. Now, what happens here? Here in the case of ferroelectric capacitance, the energy stored in ferroelectrics is governed by equation U equals to alpha by 2 QF square plus beta by 4 QF to the power 4 plus gamma by 6 into QF to the power of 6. But here I have restricted myself to only two terms, alpha and beta. Now, as I have already told you in my previous graph that how I got the values of alpha and beta. So those alpha beta values remains the same. what I have obtained in my earlier explanation. So for TFE equals to 30 nanometer, I got my alpha value as 1.4911 into 10 to the power 14 and beta value as 8.073 into 10 to the power of 41. So here I have taken y is the energy and x is the charge. So on y-axis I am having energy and x-axis I am having the charge. So if I try to plot, so here you can see, let me zoom it a little. So here in this range, you can see a inverted parabola.
Yes.
Now, if you realize the same thing for a dielectric capacitor, the radius of curvature of that U versus Q will be positive. It will the parabola will be in upward direction.
Yes.
Here, if you see for that particular range, the radius of curvature is negative, or I can say the parabola is inverted. So that also here confirms the presence of negative capacitance. The same thing which I have done for TFE equals to 30 nanometer, I am going to demonstrate for 30 nanometers, 90 nanometer and 120 nanometer.
And what about these graph in reverse direction? ये जो नीचे है baseline से,
This one?
ये जो dip up, बीच में upper dip जा रही है.
हाँ.
ये-
This is only what I am talking about. So this is like the radius of curvature here is negative. This region only tells about the
only- okay.
the negative capacitance, because here the parabola is inverted. If you
What the
just
phenomenon occurs?
हाँ.
देखिए बीच में इन्वर्ट हो गया.
हाँ.
Then ये देखिए नेगेटिव डायरेक्शन में, then
हाँ. That is because of non-linearity, in because that higher order terms are getting added. So here like it's minus, the alpha was negative, but beta is positive. And if you add gamma also, so because of that non-linearity, this kind of curve is coming.
अच्छा.
Because you are adding some positive coefficient onto that negative one.
सीधा ऐसा कब नहीं आ पाएगा.
No. That mathematically can come, but for a ferroelectric, the ideal curve will be like this only. So it will be inverted parabola for some range only, not entirely.
Okay.
Mathematically, if I erase this thing, you will get negative curvature, but that is not right. That is not for the ferroelectric material. For ferroelectric material, you have to consider all the coefficients, alpha and beta, and gamma also. But this is what should I say, second order transition material. In second order transition material, I can neglect the value of gamma.
Okay.
So that's why I have neglected for simplicity of the audience.
Order maybe increase up to third order.
Yeah, third order I can.
In that case, you have to include gamma.
I have to include the value of gamma.
Okay.
Now, the same thing, what I have done for TFE equals to 30 nanometer, I need to do for 60, 90 and 120. So let me just enable these. So again you can see the radius of curvature for each one of 30 nanometer, 60 nanometer, 90 nanometer and 120 nanometer is negative. So that confirms the presence of negative capacitance. So previously in my previous graph, I showed you charge versus voltage.
Yeah.
There also we confirmed the presence of negative capacitance, and here also we confirmed the presence of negative capacitance. But the negative capacitance state in a ferroelectric capacitor is highly unstable. And if you make a capacitor out of a ferroelectric material and analyze it using a impedance analyzer, it will show us a value of positive. Why this is happening? Because this transient, the negative capacitance state in ferroelectric is highly unstable. If you try to put charge on this slope, it automatically falls into one of the minima. And that's why when you are putting your ferroelectric capacitor in a impedance analyzer, you are not able to see negative capacitance but a positive capacitance. Now the question arises, how can we judge that my ferroelectric capacitance or a negative capacitance is present? So for that, what we need to do, we need to add a small dielectric capacitance in series to ferroelectric capacitance, which I have already told in my morning session. So let me just go to the third analysis of charge versus voltage for FEDE heterostructure. Means I have metal, below to metal I have ferroelectric, below ferroelectric I have dielectric, and below dielectric I have a metal. And let's try to understand what happens if I add a dielectric in series to it. Like these graphs which we have studied are for ferroelectric capacitor. Now the next graph which I will be discussing will be for FEDE heterostructure.
Okay.
So let me go to graph number 3.
Is it a simulator only just graphical representation?
This is
I think it is only graphical representation tool.
it's equation plotter actually.
Equation plotter basically.
So this we can
उसका
get.
कोई simulator नहीं है जो.
No, this is just means if you get the values of coefficient, you get the values x, y. If you give, it will give the
सबस्ट्रेट थिकनेस से ये कैलकुलेशन के लिए कोई टूल नहीं है.
thickness से calculation के लिए.
वो स्ट्रक्चर है बेसिकली.
हाँ, स्ट्रक्चर को हमने मैथमेटिक्स में कन्वर्ट किया है ना.
नहीं वो तो आपने अल्फाबेटिक कैलकुलेशन के वैल्यू ले ली है.
हाँ, वैल्यू ले लिया.
कोई टूल नहीं है सिमुलेशन का जिसमें वैल्यू सिलेक्ट करें और ग्राफिकल टूल कोई.
Graphical tool you can probably do in Silvaco or something,
अच्छा.
but here this is in purely mathematics.
प्योरली मैथमेटिक्स. ओके. क्योंकि ये वैल्यूज कैसे आई वो थोड़ा सा.
Which values, sir? Which values?
वैल्यू ऑफ अल्फा एंड बीटा.
Alpha that
That is
that
from
is
formula,
pen
from-
and paper
पेन एंड
calculation.
पेपर कैलकुलेशन.
Calculation.
अच्छा. ठीक. ओके.
Now,
वो तो फार्मूला है उसमें वैल्यू पुट अप किया आपने.
yes. And same thing you can do using MATLAB also. Actually, what has happened? We have converted that structure into
MATLAB
equation.
is not required. It is
Ah.
a formula based thing.
Yes.
You just put the value.
Yes, very correct.
It is not required.
Yes.
Okay.
So that's why, for simplicity of the students and the audience, I have selected Desmos. Because we guys may be from different backgrounds. Some guys know MATLAB, some guys don't know MATLAB. So for simplicity of audience, I have selected Desmos. So same thing can be done using MATLAB also. Simple, you have to write an equation and just ezplot command is there. You can use that ezplot command.
That is not required.
Not
Simply you can-
So now this is the FED heterostructure. Now if you see properly, this y equals to 1.593 into 10 to the power minus 15 into x. This is the Q equals to CV. This expression is Q equals to CV, and this is the case for TFE equals to 0. TFE equals to 0 means there is no ferroelectric, only dielectric is present. So no need to make a use of LK equation, because at present I am having only dielectric. Why I need to use that LK equation?
Value of C is 1.593.
Yes, the value of dielectric capacitance, which I have as in the morning session I have told you that the value of permittivity I have taken as 4, which is SiO2. Epsilon naught you can use 8.85 into 10 to the power minus 12 farad per meter. A value is 45 micrometer into 1 nanometer. So, sorry, 45 nanometer into 1 micrometer. And thickness is 1 nanometer. So if you solve it, you will get the value of CD, that is dielectric capacitance, equals to 1.593 into 10 to the power minus 15.
Simple formula C equal to epsilon A by D.
Yes. Just you have to put the values and you will get the value of value as 1.593 into 10 to the power minus 15. Now this is Q equals to CD.
So on y-axis we are plotting Q. On x-axis there is
V.
Okay.
So this is Q equals to CV, where C value is this.
And it is x.
This
It
is V.
basically.
So you can see this linear characteristic.
Okay.
So
It is for dielectric.
dielectric. So let's see it only in, because mathematics may give negative also.
Okay.
So we'll see in first quadrant only.
Okay.
Now, as both the capacitors are in series to each other, So now the modified equation will be what? We have to get the modified equation. So what I have done, so now this equation modifies to alpha QF plus beta QF plus QF upon CD equals to Vs. Because now this is a heterostructure and you have some value of ferroelectric thickness. When ferroelectric thickness is there, you have to include that LK equation. Now this is my equation. Alpha QF plus beta QF cube plus QF upon CD. CD is 1.593 into 10 to the power minus 15 equals to X. X is nothing but my supply voltage. So you can see the curve is something like this. So here there is no signature of negative capacity. Gamma is not included. For simplicity, I have neglected gamma because this is a second order transition material. Ferroelectric materials can be classified, sub-classified into second order transition and first order.
Another parameter, that is y upon 1.593 into.
That is for because here I have considered that dielectric thing.
Yes. Okay. It is actually
Heterostructure. It is combination of.
That's why you have. Okay. Yes,
Aslam. Here it is a combination of ferroelectric and dielectric capacitor, so that's why this equation is like this. So now you can see the red curve. The red curve it signifies there is no, here slope is not negative, it's positive. And if you see properly, the capacitance, because this is nothing but charge versus voltage, correct? On y-axis I am having charge and on x-axis I am having voltage. And capacitance is nothing but
QIV.
So Q equals to CV, so capacitance equals to dQ by dV. So this capacitance is higher as compared to this.
Yes.
This capacitance is
yes.
higher as compared to this. And if two positive capacitance are in series to each other, their equivalent will be C1 into C2 upon C1 plus C2. And obviously the equivalent capacitance will be less than each of them.
Yes.
But here if you see properly, that red curve has more slope as compared to the purple curve.
Yes,
so that confirms the presence of
negative
capacitance. The total capacitance of the heterostructure has increased.
Okay.
Now the same thing happens with the other thickness also. So this is for TF equals to 30, 60, 90 and 120. Just a second.
Clear. We will consider all these parameters up to that particular convergence point only.
So just a second, I'll come on to that. So if you can see for all the 4 values of thickness, there is a increase in capacitance. So as you are asking, because amplification is only available till here.
Yes.
So because this is happening because of non-linearity of ferroelectric capacitance. Like dielectric capacitance, ferroelectric capacitance is non-linear. Dielectric capacitance is linear, Q equals to CV. But in ferroelectric capacitance, what is happening? Vf equals to alpha QF plus beta QF to the power of 3 plus gamma QF to the power of 5. So this is non-linear. So that's why it is intersecting at some point. After that, there is no amplification.
Yes.
So if you see after this point, there is no amplification visible. So amplification is there only up to this point. So this signifies the presence of negative capacitance and capacitance enhancement also.
Yes.
So this we have seen the curve charge versus voltage for heterostructure.
Okay.
Now I'll move on to U versus Q.
Okay.
Like we have discussed the energy versus charge for isolated ferroelectric
Yes,
capacitor.
clear.
And now we'll move on to U versus Q of heterostructure. Now this is
the perfect graph.
now if you can see this.
Now this is the perfect graph.
Yes. So these are the graphs for FED heterostructure. Now you can see y is on y-axis I am having energy,
Yes.
and x-axis I am having charge.
Okay.
So as both the capacitors are in series to each other, so U total will be equals to U of ferroelectric plus U of dielectric. So U of ferroelectric we have already studied in my previous isolated capacitor, isolated ferroelectric capacitor, and U of D will be what? U equals to Q square by 2C. So this I have written here, U equals to Q square by 2C. Now alpha value I already know for TFE equals to 30 nanometer. Beta value I already know for TFE equals to 30 nanometer. This CD value I already have, which is 1.593 into 10 to the power minus 50. So this red curve represents the energy versus charge for heterostructure with ferroelectric thickness equals to 30 nanometer.
Hello.
So as we move on, keep on increasing the thickness, if you are able to see, like the next case is for TFE equals to 60. The next case again is for TFE equals to TFE equals to 90 nanometers, and the next case is for TFE equals to 120 nanometer. Now what is happening? The interesting thing what is happening in this curve is the curve is starting to get flatter. So if you see the purple line, purple line is more flat towards the y-axis. Towards the y-axis. So more flatter, the curve, if the curve is flatter, means the capacitance is increased, because there is a relation between energy and charge. You can write U equals to Q square by 2C, and C equals to what? If you solve this, that becomes D2U by dQ square inverse. So more flatter means more energy and higher capacitance.
Okay.
So if you can see the purple line, which corresponds to TFE equals to 120 nanometer, the capacitance has increased, and which is not possible in the case of normal dielectric or two positive capacitors. So this explains me that there is something called negative capacitance present over here. That is why the total capacitance has enhanced. Otherwise this is not possible in normal positive capacitance. So there were two ways through which I can confirm the presence of positive capacitance. One was capacitance, and the second was voltage drop. So in these two curves, I have focused on how the capacitance is getting increased. Like here, the curve is flatter, so capacitance is more. And in the previous one, because the slope of that charge versus voltage characteristic for TFE equals to 120 nanometer was higher, so I can say the capacitance is higher. Now, the thing is, the next part is I have to focus on voltage drop. Like if two positive capacitors are connected in series, what happens? The voltage drop across one of the component will be obviously one or both the components will be less than the supply voltage.
Yes.
That is as per the Kirchhoff's voltage law.
Yes.
The voltage drop across the component equals to voltage applied. So if voltage applied is Vs, voltage drop across ferroelectric is Vf, and voltage drop across dielectric is Vd. Qf equal, so I can write Vs equals to Vf plus Vd. Now, if somehow I get Vd means voltage drop across dielectric is more than the supply, that becomes an interesting case. And that interesting case is possible only when there is a presence of negative capacitance. Without that, that is not possible. So let me just move on to graph number 5. So this is my graph number 5. So let me just, now, so on y-axis I have Vd. Vd is voltage drop across dielectric, and on x-axis I have Vs, that is supply voltage. Okay, so I have taken one Vs for reference. Vs equals to y equals to x. It's a straight line, so that I am able to judge where is the amplification and where is amplification is not present. So I have written an equation for heterostructure. So x in x-axis, as I just told, this is x-axis I am having. V S.
This red line is for y equal to x.
Y equals to x. Simple, linear relation. So because I have to understand whether I am getting amplification or I am getting attenuation. Just for reference I have taken. So now this is the equation which I have got, and the equation is Vs equals to alpha. You can see this is my parameter alpha, which I have been telling in all these graphs. This is alpha for TFE equals to 30 nanometer. I have CD with me. This is CD.
Okay.
This
Here
is
you have multiplied it.
Multiplied it. That means if you write and solve this equation you are going to get.
Okay.
The equation is Vs because in y axis.
It is equal to x actually.
Yes.
In that case, that is equal to y.
Y, yes. So if you solve it, so for TFE equals to 30 nanometer, like if I see at 5, let's see at 5. So y equals to x means the voltage drop across dielectric is how much? Same.
Okay.
Just see the coordinates, x and y coordinates are same. Now let me just go to TFE equals to 30 nanometer.
Okay.
Now just see the x coordinate. X coordinate is 4.972
Okay.
and y coordinate is 5.72. So that means I have applied 4.92 and I have got 5.72. Just here, like just see here. X coordinate was 4.61. So supply voltage is 4.61 and I have got voltage drop as 5.38. So that tells me about the amplification.
Okay.
I am applying the supply voltage is less and the voltage drop across dielectric is
More.
higher. And the same thing is observed in the other
Every
characteristic also, in every graph. Like here, let's see.
No, in
So it's
every graph.
in every graph it is there, 7.07. So what we can conclude from here is the negative capacitance state in ferroelectric is highly unstable. Although mathematically we can see the signatures of negative capacitance in the ferroelectric, but if you make a capacitor out of the ferroelectric material and put it in a impedance analyzer, you will see a positive capacitance. So in order to visualize or in order to have a proof of negative capacitance, there are two ways. One is you check for total capacitance and the voltage drop. Now, as I developed the equations for
Voltage drop.
FED heterostructure, the capacitance in both the cases, we found like the capacitance in charge versus voltage and capacitance in U versus Q, energy versus charge, was higher.
Yes.
So that is only possible if some negative capacitance is there. Otherwise, it is not possible because it violates the normal law of thermodynamics or normal laws of Kirchhoff's voltage law. Similarly, the second way to confirm the presence of negative capacitance is voltage drop across one of the component. As Kirchhoff's voltage law says, the voltage drop cannot be greater than the supply. But here, I have got my voltage drop across one of the component
That is
higher than the supply voltage. So this
for dielectric, no?
which one, sir?
This particular graph, these graphs, which
Uh,
type of capacitor?
So this is heterostructure. Heterostructure.
नहीं, which voltage drop across which capacitor?
Dielectric capacitor.
Dielectric है, वही मैं कह रहा हूँ.
This is a normal graph, Vs equals to Vd. And this is the graph for heterostructure with TFE equals to 120 nanometers.
Okay.
And below 1 is 90, 60 and 30.
Okay.
So this confirms the presence of negative capacitance. So this was it about the lab session. If you have any queries, feel free to ask.
Sir, can we use this Desmos for some publication, or it is the only study tool?
It's like you can just get the confirmation. But for publication and all, you may have to refer to MATLAB. You have to plot this because it's user friendly. That's why I have gone for Desmos.
We
So-
cannot use it in paper.
For that, you have to plot these graphs in MATLAB. But MATLAB also, it hardly takes any time. You just have to write the equation and you have to use the command ezplot.
Yes.
For my publication purpose, I have used MATLAB and I got the graphs in the MATLAB. So using this, just you can get confirmed because sometimes MATLAB becomes tedious. So you just, what I usually do is I write the things in Desmos, I get the confirmation, okay, yeah, it is coming. And once I confirm that everything is going in right direction, when I have to write the paper, I'll plot everything on MATLAB and then,
Just,
this is just for confirmation. But this is a good tool. Exactly same thing will be replicated in MATLAB also.
How is there any further part then how we will use it in MOSFET?
So MOSFET, it's like now the purpose of studying that this FED heterostructure is, it is giving us passive voltage amplification. So means I'm applying small voltage and instead of applying a small voltage, I'm getting a high voltage at dielectric. Now consider a situation, I have a MOSFET. MOSFET means MOS, below I'm having substrate, top to it I'm having a dielectric, and above dielectric there is a metal. This is my MOSFET, MOS structure. Now, when I'm trying to design NCFET, negative capacitance field effect transistor, so how the arrangement will be? First there will be a semiconductor. Above that there will be a oxide, which is a dielectric oxide. Above to that there will be a metal. Above to that I'll keep a ferroelectric, and then again a metal will be there. Now, what we have studied here, the voltage drop across the dielectric is higher as compared to what you supply. Now in MOSFET what will happen? Because I have a metal, ferroelectric, metal, dielectric and then semiconductor. Now if I apply something onto gate, let's suppose some value, X value I have applied. So voltage drop across dielectric will be greater than X. And once it is greater than X, so you can
Initial current.
So you can assume your MOSFET, NCFET as a normal MOSFET with an amplifier. And this is what I was talking in the morning session about passive voltage amplification using NCFET, using FED heterostructure. So just suppose you are applying some X value at the gate, and at dielectric you are getting greater than X. So it is,
I'm asking you,
it is highly advantageous for us.
You discussed it previously in your session. What I want to know, is there any graphical presentation that you can compare both the cases?
Which
Both
two
the
cases? So
MOSFET without
tomorrow's session is for that only. So everything will be with respect to MOSFET and NCFET.
Okay.
Because this session, in today's session, what I had done is I have just told you about how this heterostructure is, what is the purpose of heterostructure. Now once the audience knows these all things, so it will be easy for them to understand what is happening inside NCFET. So it's like a building exercise for tomorrow's lecture.
Yes,
Basically
there will be a
building
performance
exercise.
comparison
So
of
it's
NCFET
like
and
putting one
simple
brick.
for MOSFET.
If I am building a wall, I am putting one brick at a time. So like today we have laid the foundation, then we'll be putting the bricks and we'll be having the building tomorrow.
Okay. Thank you, sir.
If you are having any queries, please feel free to ask.
So all the things are clear. Sir, do you have any query?
Any question? कहाँ पे हो?
It is clear.
Okay, so
हाँ.
this is it for today's lab session. So tomorrow I think I have one session. Okay, so next things will be discussed tomorrow. Okay, thank you so much.